Okay, so it's my pleasure to introduce Dr. Brian MacIntosh at this seminar for our research team. I don't remember the exact name, exercise physiology and nutrition. It's not the name, it's something like that. Caroline, may know it. Anyway, so Brian graduated in 1979 from the University of Florida. Title of his dissertation was Fatigue in Skeletal Muscle. So from 1980 to 86, he was an assistant professor in the Department of Exercise Science at Concordia University. And then after that, he moved to the University of Saskatchewan as an assistant professor until 1989, when he moved to the University of Calgary, correct? And so he came as an associate professor, and he's now, as you know, a full professor. So among other things, Brian was an associate dean, graduate faculty of our faculty as well, and I didn't know that associate dean in the Faculty of Graduate Studies. And more recently, and I'm not listing obviously the CV like 40 pages long, so I'm going to make it short. He chaired the National Advisory Council for Exercise Medicine in Canada. So I think that was a very important position. He got numerous awards, and again, I'm not going to list everything, but correct me if I'm wrong. I think one of the most important ones for you was the honor award that you got from Canadian Society for Exercise Physiology 2 years ago. I was there, so it was very nice. And he was also president of this society between 2007 and 2009. And also associate editor for the journal of this society for almost 10 years. I'm not going to provide your funding, and same thing in terms of the list is too long. In terms of papers, so you have 75 articles in various journals, not only in physiology but in biomechanics as well. I still remember, and I think those, more than the number, it's the quality of the papers, I would say, is more important. I still remember the paper that you published with Rassier between the quest distance of potentiation and fatigue. I think probably not the highest impact journal, impact factor, but a very important paper, very interesting one. And I have to say that I often cite some of your papers in my lectures. And not only when I talk about fatigue, or more basic exercise physiology, and I think this is very important to mention. 13 book chapters. He was the editor with Beno and the Master of Biomechanics and Biology of Movement, published by Human Kinetics in 2000. And Brian was also the author with Gardner and McThomas of an important textbook called Skeletal Muscle, Form and Function. Very nice book. You have a chance to read that. Brian is, correct me if I'm wrong, there are a few former students supervised by Brian. He supervised more than 30 graduate students during his career. So overall, you can see excellent CV, but in my opinion, this CV only partially reflects your knowledge in exercise physiology. You're one of the most knowledgeable exercise physiologists that I know. I'm serious now, and I know quite a few.
Well, thank you for that brief introduction. Actually, let me go back to the start here. And there's no seat left for me. So the title is a little bit vague here. I thought I'd try to stir up some interest or talk about a couple of things that I thought showed that it's important to look very carefully at your data and perhaps even ignore the interpretation from other people of data. And I've always believed that the data that are published are correct. The interpretation may need some work. And I think that's an important lesson for everybody. So this just kind of summarizes the work that I've done at the University of Calgary. I've studied really two different fields skeletal muscle contractile properties using primarily the rat gastrocnemius muscle, and several topics in exercise physiology. And when I first came to Calgary, I did some work on peak power output, which was basically the Wingate test, but we actually instrumented the cycle ergometer so we could measure power output continuously and looked at the force velocity properties of cycling. And that kind of gave me some insight into considering submaximal exercise and the impact of the force velocity properties of the motor units recruited, which is an important consideration. I've looked at fatigue in both the isolated muscle preparation as well as in whole body exercise. And in, I think it was 2008, I was engaged in a debate with Timothy Noakes over the peripheral and central governor. That was one of the sessions at the Canadian Society for Exercise Physiology meetings. More recently, I've done some work on the energy cost of running, which I could actually give the whole seminar on that, but I'll let Jared do it because he's the one who did most of that work. And I've also done some work on warm-up, and I will touch on some of that. But one of the interesting things that we've done recently, and this is Jamie Weir and Jessica O'Connell, have done work on the slow component of oxygen uptake, and in my opinion, have redirected the direction that research in that field should go. So, that's having fresh eyes that look at something helps it to create that direction. So I'm going to focus on that initially, and then time permitting, I'd like to look at another issue, which is calculation of active force in skeletal muscle. And several years ago, we realized that people are subtracting the wrong passive force when they calculate active force. So I'll go through some of those observations as well. Guillaume mentioned this book, which I had the pleasure of working on with Benno several years ago. And in the course of producing this book, I actually wrote a few chapters, and one of them dealt with the energy cost of cycling exercise. And as part of that, I looked at the slow component of oxygen uptake because it's an important aspect of energy cost of cycling. The slow component is actually an increase in oxygen uptake beyond the time when you would normally think a steady state should have been achieved. And that slow component can account for an increase in oxygen uptake of a few hundred milliliters per minute and up to in excess of 1 liter per minute. It typically occurs when the exercise intensity is above the anaerobic threshold. And what's characteristic about the anaerobic threshold is that any intensity above that threshold involves continued anaerobic energy contribution. Now, several theories have been proposed, and when I wrote that chapter, I actually looked at all of the current theories and evaluated the evidence for them, and wrote in the chapter what I thought about each of those bits of evidence. So this just shows the slow component of oxygen uptake, which would begin about here. Okay, that's not... begin about here. And actually, the original definition of the slow component was that any increase in oxygen uptake beyond about 3 minutes was the slow component of oxygen uptake. And that was because we thought that by 3 minutes, you should reach a steady state. More recently, people have been curve fitting a 3 exponential equation, one for phase 1, which is the early increase. I'm not going to go into the mechanism there. Phase 2 is the rapid increase in oxygen uptake over the first minute or 2 of exercise. And then phase 3 would be constant with no increase if you're below anaerobic threshold, but has this progressive increase when you're above anaerobic threshold. And there were several theories that I looked at when I was writing this book chapter. We knew at that time that 80% of the increase was in the legs. And this was actually determined by David Poole, and he cannulated arteries and veins and measured leg muscle oxygen uptake while he measured pulmonary oxygen uptake, and realized that most of the increase was actually coming from the legs. people at that time, this is before 2000, thought that getting rid of lactate would cost energy. And so it was considered to be a factor. And like I said, there is anaerobic energy contribution above anaerobic threshold. So it seemed reasonable to think that lactate was causing the slow component. The thing is, though, lactate is a substrate just like glucose. It can be oxidized. It doesn't cost energy to get rid of it. So they showed that if you actually infuse extra lactate, it doesn't increase the oxygen uptake. So lactate was ruled out as a factor contributing to the slow component of oxygen uptake. Some people thought, well, when you exercise at this high intensity, you tend to warm up. Warming up the body will increase resting metabolic rate. Maybe it will increase the exercise metabolic rate as well. And people evaluated this by looking at pre-warming the individual to see if you could get a greater increase, or cooling them during the exercise and see if you can get rid of the slow increase. Neither of those worked. So the Q10 effect of temperature was ruled out. It was also suggested that catecholamines might be important. We know that catecholamine concentration in the blood increases when you exercise above anaerobic threshold. In fact, some people have said it's a catecholamine threshold, not an anaerobic threshold. But if you actually infuse extra catecholamines, you don't increase muscle oxygen uptake. So that was ruled out as well. So the last point here, the recruitment of less efficient motor units, has been thought to be, ever since 2000 and perhaps even before that, has been thought to be the major contributing factor to the slow increase in oxygen uptake. And it's thought that fatigue is occurring in the muscles that are exercising. And when fatigue occurs and you're exercising at a constant power output, you have to recruit additional motor units just to maintain that power output. And if you're recruiting fast twitch motor units, they were thought to be less efficient than slow twitch motor units. And so that would contribute to an increase in the energy cost of the exercise. And just to kind of explain this efficiency idea, this is a graph of oxygen uptake versus pedal rate at different power outputs. And you can see that the oxygen uptake increases as you increase pedal frequency from about 50 to 120 revolutions per minute when the power output is 100 watts. 100 watts is pretty easy. You don't have to work very hard to generate 100 watts. And the fact that it increases is probably because as you increase the cadence, the velocity of contraction of, it should be slow twitch motor units that you're using at this low power output, the velocity of contraction increases and the efficiency actually decreases. And this is actually related to the relationship of force and velocity, or power and velocity. And if you go up to a velocity of shortening in a muscle where the power output is decreasing, the efficiency will also decrease. And so it can be easily explained that slow twitch fibers have an increased energy cost when you increase the cadence. What's really interesting here is that if you look carefully, as you increase the power output, the lowest oxygen uptake occurs at a cadence that's progressively higher as power output increases. And it's thought that this is because as you recruit type 2 motor units, type 2 motor units have a best efficiency up in excess of 100 revolutions per minute. And type 1 have a best efficiency around 50 revolutions per minute. And so as you recruit type 2 motor units, now your efficiency tends to creep up towards that 110 or 120 revolutions per minute. And it all relates to the force velocity and power velocity relationship. And these, the lines on the top graph here show recruitment of additional motor units and the change in the force velocity relationship that would occur, and the corresponding change in power output if you plot power versus velocity. And one of the things that is evident when you look at this, if we look at 100 watts power output, if I can get that laser point there, at a cadence around 50 RPM, somewhere around there. If you increase the cadence, you have to recruit more motor units because you go above that line. And we know that when you're cycling, you're not activating all of your motor units. And I knew that from my earlier work on peak power output. Peak power output in most athletes, and particularly sprint athletes, is in excess of 1,000 watts. Power output where anaerobic threshold occurs is down around 200, maybe 150 to 300 watts, depending on whether you're looking at males or females and conditioned endurance athletes or not. So we're really submaximal here. We're not recruiting all of the motor units, but there's a chance that we are recruiting some fast twitch, so that might influence the maximum velocity and the power output where the best, the cadence where the best power output will occur. And the power velocity relationship actually looks very similar to the efficiency velocity relationship. As you recruit additional motor units, the cadence where your best efficiency will be keeps increasing. This just shows the recruitment of additional motor units. Looks like the oxygen uptake cadence relationship. And basically, again, the minimum motor unit recruitment will occur at progressively higher cadence as you go from 100 to 200 to 300 to 400 watts. And that's because as you go to a higher power output, you're recruiting some fast twitch motor units, and now the minimum is going to be at a higher cadence. So that background just helps you understand why, as you recruit fast twitch motor units at a constant power output, the energy cost might increase if you're cycling at a constant low cadence. So I thought it would be important to do a study where you evaluate the slow component at a high cadence. So you have somebody cycle at a constant power output above anaerobic threshold for 5 to 10 minutes and evaluate the slow component of oxygen uptake. If they're already at a cadence where efficiency is high for the fast twitch motor units, there shouldn't be a slow component. Now, unfortunately, I didn't get around to doing that study, but a few other people did. And what's remarkable about these studies is that in all three cases, the slow component got larger when they cycled at a high cadence. This argues against the idea that type 2 motor unit recruitment is the cause of the slow component of the oxygen uptake. So that left us with no satisfactory explanation for the slow component of oxygen uptake. And I started to question whether or not it was real. Now, that might seem rather extreme, but the important thing to remember is we were measuring oxygen uptake, and we thought an increase in oxygen uptake meant an increase in energy cost. We weren't measuring the anaerobic part. It was just assumed to be there and assumed to be constant. So we know that lactate accumulates when exercise intensity is above the anaerobic threshold. And so there is continued anaerobic contribution. But what we don't know is whether that rate of accumulation is constant. And so Jessica O'Connell did her thesis where she asked the question, does the total cost of exercise remain constant beyond that needed for the increase in ventilation? We knew that an increase in ventilation would contribute to the slow component. So there was going to be a small slow component because of that. But if we measure the anaerobic contribution, will it actually decrease over time? So she did a series of studies where she measured oxygen uptake for, now the first part here is warm-up, and then they actually increased their power output to an intensity 60% of the difference between a lactate threshold and maximal oxygen uptake. And they cycled for either 3, 6, or 9 minutes. And she measured oxygen uptake during this time. Now this graph just shows how consistent the measured oxygen uptake was in the 3 separate trials that were 3 minutes, 6 minutes, or 9 minutes, always at the same power output. And this shows that ventilation actually increased. And it increased quite a bit. Now, to compensate or at least account for the increased energy cost of ventilation, she quantified the ventilation, she calculated the work of breathing based on equations from the literature, and estimated the equivalent oxygen uptake for ventilation. And she subtracted that from her measured oxygen uptake. And then she also, in the previous slide, she measured lactate, blood lactate before and after the 3-minute ride, before and after the 6-minute ride, and before and after the 9-minute ride. So she had lactate accumulation in each of those 3 rides. And if you subtract the accumulation in the 3-minute ride from the lactate accumulation in the 6-minute ride, you get the lactate accumulation from 3 to 6 minutes. And if you subtract the accumulation in 6 minutes from that in 9 minutes, you get the accumulation for the last ride. And then what she did was she calculated the anaerobic contribution from that lactate formation, and this actually shows the blue is ventilation increasing, the green is the subtracted oxygen uptake for ventilation, and then the reddish or rust color is the estimated energy cost contributed by lactate accumulation. And there are published values in the literature that give an oxygen uptake equivalent for a given change in blood lactate, and that's what she used.
Would you mind doing the colors again?
So the blue is measured oxygen uptake.
So that's the data you already showed.
Yep. The green is, well, actually, the blue is the measured oxygen uptake minus the green, which is the oxygen uptake for ventilation. And then the red, or the rust color, is the oxygen uptake equivalent of the lactate accumulation. And the oxygen uptake was measured continuously, breath by breath, and then estimated every 10 seconds. The lactate was only measured at 3-minute intervals. And so what she did was she put in these bars to come up to a constant value for the first 3 minutes, a constant value for the next 3 minutes, and a constant value for the next 3 minutes. And then she's added the green lines on top just to show how much she had subtracted from the oxygen uptake to get the blue lines. And this is just a single subject. This is the mean data. And so what you see here is the blue is aerobic and the red is anaerobic based on lactate accumulation. And from 0 to 3 minutes, 3 to 6, and 6 to 9 in her, I believe she had 8 subjects. And the remarkable thing is that the total energy cost does not increase from 3 to 6 to 6 to 9 minutes. That's when it was thought that the slow component of oxygen uptake was causing an increase in oxygen uptake. The fact that the initial 3 minutes has a smaller total energy cost than the next 2 is probably because of what we call the immediate energy system, so a decrease in creatine phosphate concentration and some energy provided by oxygen stores that are in the body, which does not get accounted for when you're measuring oxygen exchange across the lungs. So the key observation here was no change in total energy cost of the exercise. So there's no need to explain the slow component of oxygen uptake based on an increased energy cost of the exercise. And Jamie followed this up with another study, basically confirming what Jess had seen, but looking in particular at the impact of a high-intensity warm-up on performance of this exercise. And what she did was she had a warm-up initially that was either a moderate intensity or a heavy intensity, and this heavy intensity was almost as high a power output as the actual trial. And again, she had them do 3, 6, and 9 minutes on separate days at this high intensity that should elicit a slow component of oxygen uptake. And this is her data. And I'm going to actually, she has accounted for the immediate energy system. And the way she did this was to measure the recovery oxygen uptake after the 3 and the 6 and the 9 minute exercise. And it's thought that the recovery oxygen uptake can be divided into 2 parts, a fast part and a slow part. The fast part correlates very well with the provision of energy from the immediate system and stored oxygen. And so with that, she estimated how much energy was coming from the immediate system, and that's the green. And you'll notice that most of it is in the first 15 minutes. There is actually a little bit still in the next 15 minutes, and then none in the last first 3 minutes. So a lot in the first 3 minutes, some still in the next 3 minutes, and none in the last 3 minutes. The red here, or orange as it looks, is the anaerobic contribution from lactate formation. And again, most of that is in the first 3 minutes, a little bit less in the next 3 minutes, and much less in the last 3 minutes. And what is evident here is that the high-intensity warm-up, which we knew should decrease the slow component of oxygen uptake, actually decreased the anaerobic contribution. So the heavy warm-up, that's in the first column here, in the first 3 minutes, it decreased the anaerobic contribution and increased the aerobic contribution. And that's because a high-intensity warm-up increases the rate at which oxygen uptake will increase in a subsequent bout of exercise. And by having exercise with a higher rate of rise of oxygen uptake, you need less lactate formation. And so the anaerobic contribution of the lactate was actually a little less.
Now, isn't this missing that jump you said that happens at 3?
Missing the jump?
So before you showed that there's a lower cost for 0 to 3, and then from 3 to 6 and 6 to 9, it's higher but constant. And then this looks like it doesn't have it.
That's because she's quantified what was missing, which was the immediate energy system in green. So just to go back, there's no green back here. And so we thought that the green would fill up the difference here. And Jamie showed that, yes, it did. And in fact, it looks like it's even more than enough. So either she's overestimated the immediate energy system, or there's actually a higher energy cost in the first 3 minutes than there is after that. But again, no increase in total energy cost after 3 minutes of exercise when the slow component of oxygen uptake is developing. And you can see that, now again, she's subtracted the energy cost of ventilation, or the oxygen equivalent cost of ventilation, and you can see that the aerobic part is going up from the 3 minutes to the 6 to 9 minute, and the anaerobic part is going down. So it's just a switch between the energy systems that explains that slow increase in oxygen uptake. So just to conclude from that work, the slow component of oxygen uptake does not represent an increasing energy cost of exercise. Rising oxygen uptake corresponds with falling anaerobic contribution based on the smaller lactate accumulation in the 6 to 9 versus the 3 to 6 minutes. So heavy intensity warm-up increases the aerobic contribution early in the subsequent exercise, diminishing the anaerobic contribution that's required without changing the overall energy cost. The slow component is therefore decreased by heavy intensity warm-up because of the lower initial anaerobic contribution. And if the slow component is the decreasing anaerobic and increasing aerobic, if you start with less anaerobic, you've got less to decrease. So the slow component is smaller. And let's see, I can't see the time because it's so got a reflection there. So I think I have lots of time. I'm going to go to the second example. That's the slow component of oxygen uptake. And I think because I had done all of that extra reading in preparation of that chapter, I had a better understanding of what mechanisms might contribute to the slow component, and that actually led to the idea that maybe it's not real. So now I'm going to talk about calculating active force in skeletal muscle. So when I was a graduate student, I was studying skeletal muscle, and I was taught that you you measure the peak force during a contraction, and you subtract the passive force, and that gives you the active force. And I'm going to call this the traditional way of calculating active force. Everybody, or almost everybody, seems to do it this way. I actually found 4 papers who did it the way I'm going to get to in a minute, or several minutes. But most people calculate active force this way. It seems to make sense. But even when I was a graduate student, I would often think about the interaction between active and passive and think, you know, we're trying to, in estimating the active force, we're trying to figure out what the cross bridges are doing. Passive force is caused by a number of structures within muscle. If you have an isolated myofibril, titin is providing most of the passive force. If you have a whole cell, then the membrane is actually contributing to that passive force. If you have a whole muscle, then there's all kinds of connective tissue in the muscle that contribute to the passive force. So this is the actual muscle preparation that I've used. I used it at Concordia University when I was working with Phil Gardner, who was actually from University of Montreal at the time. And the rat gastrocnemius muscle is relatively easy to isolate surgically. And what we do is we fix the bone, the femur and the tibia, so that the origin of the muscle can't move. Stimulate the sciatic nerve, but we've cut all of the branches of the nerve that go to other muscles. So we're only stimulating, now it used to be the whole gastrocnemius, but more recently I've done the medial gastrocnemius alone. And then the Achilles tendon is attached to a muscle lever. This one happens to be a pneumatic lever, but it can be made isometric by having a high load, or in some cases we've just used an isometric force transducer. I was interested in the length dependence of fatigue. And it's odd, but muscle seems to fatigue more when you stimulate it at a long length than when you stimulate it at a short length. But if you cause fatigue and then measure force across a broad range of lengths, fatigue seems to be greater at short lengths than at long lengths. And if you go through the literature again, this is fascinating, because people come up with all kinds of strange explanations for how fatigue should be greater at short length than at long length. And one of the theories was that the cross bridges that are active during the contraction are the ones that get tired, and if you change the length, you're now allowing fresh cross bridges, and so there's less fatigue there. Somebody even suggested that fatigue dissipates when length is changed. And that actually relates very closely to the previous one, where the fresh cross bridges have better strength. This is the kind of force-length relationship that I'm talking about. Now, this shows tetanic contractions at the top and twitch contractions here. And in both cases, it's before and after, or before and after fatigue. And this also shows passive force out here. And what's really interesting is that when you go to a long length, and it's too bad they didn't do it for the tetanic contractions, but when you do that for these twitch contractions, there's no fatigue at the longest length when you measure with just a single activating pulse. And yet there's lots of fatigue at shorter lengths. So this is one aspect of the length dependence of fatigue. Well,
but maybe that's just because there's no force, no active force, right? Because isn't the passive force explaining everything at, you know, their rightmost extreme?
This is active force, and so the total force would have been up here, okay, and they've subtracted the passive force. Yeah. So this is the theory that I came up with to try to explain the length dependence of fatigue. That repetitive contractions will actually stretch the series structures, making fascicle length shorter at any given muscle tendon length. And this would actually shift the force-length relationship and could explain why there's no apparent fatigue at long lengths. So this was Meredith McNaughton's thesis, and she used sonometric crystals embedded in the muscle to measure fascicle length. and she observed the fascicle length relationship before and again after fatiguing stimulation, and the fatigue was actually 5 minutes of intermittent 50 hertz contractions. And this is the force length relationship she got, so it's exactly the same. This is active force. She has subtracted the passive force in the traditional way. Passive force measured right before each contraction. And here there was a significant difference between before and after at each of these lengths, but not out here. And here they're getting very similar. But Meredith was a pretty good student, and she wasn't satisfied with just looking at active force. The day that she showed me this graph, she also showed me this one. This is passive force measured before and after fatigue, and obviously she's got 4 different measures of passive force. It's obvious there, but not here. In the rat gastrocnemius muscle, there's very little passive force until you get up to what I now call reference length. I used to call it optimal length because it was the length that gave the strongest contraction when you calculate active force in the traditional way. And so I thought, well, okay, if you calculate it a different way, that might not be the optimal length, so I'm going to call it my reference length. But when you go beyond that reference length, the passive force actually increases quite dramatically. And what she showed was that the first time she measured force-length relationship, passive force was pretty high. And I think the multiple measures here have to do with she measured it for twitch, double pulse, and 50 hertz contractions at each time point before and after fatigue. And so what she found is that passive force was actually decreasing. Now, passive force was decreasing, but the fascicle length wasn't changing at a given muscle tendon unit length. So something going on in the muscle, lower passive force. And I looked at this, and because I had, as a graduate student, thought a lot about, are we calculating active force correctly? What's going on in the interaction between active and passive? And I saw this, and I realized we're calculating active force the wrong way. There must be something better to do in calculating active force. In other words, active force is probably changing during a contraction. And if you look at this model of what muscle is doing, if the parallel elastic is actually causing the passive force as you stretch the muscle out. Now, obviously, the series elastic will also contribute to passive force, but they have to be the same here and here, assuming the contractile element is contributing very little passive force. But during a contraction, the series elastic will get stretched and the parallel elastic will shorten. So if the parallel elastic was contributing passive force at its long length, during the contraction it's shorter, it shouldn't be contributing passive force. And yet we're adding that passive force, or pardon me, we're subtracting that passive force to calculate what the cross bridges are doing. So we had to come up with a way of proving that we were subtracting the wrong passive force. And we came up with a design that was to compare repeated contractions with no fatigue at a short length where passive force won't change, and then the same sequence of contractions at a long length where you get stress relaxation. And if you take the gastrocnemius muscle in the rat and you stretch it out to a long length and hold it there, the passive force drops fairly quickly. So that's what we were looking for. And this just shows that what we did actually found that. So the contractions were actually double pulse contractions at 20-second intervals. So each time point here represents a contraction. The passive force at the short length, and this was actually at the reference length, so not a really short length, passive force was around 0.2 newtons. And the peak total force really didn't change. It actually increased a little bit. When we stretched it out to 2.4 millimeters, passive force increased quite a bit, but decreased when we went from the first to the second, and then it didn't change anymore, and peak force was pretty constant. When we stretched it out to 3.6, the passive force started very high, but fell dramatically over the course of those 4 contractions, but the peak total force didn't change. Now, my assumption here is that when there's virtually no passive force, the total wasn't changing, so the active force wasn't changing as a consequence of doing 4 double pulse contractions. And double pulse just means 2 stimulations really close together. So it's like getting a super large twitch. And there's no reason why the force would change over the course of 60 seconds as a result of this stimulation. But if you go to this data and you calculate active force by subtracting the passive, you're subtracting a progressively smaller number, which means the active force will seem to be getting much bigger. So I think this shows that it's not appropriate to calculate active force by subtracting the passive force measured right before the contraction. We did it another way as well, and that was to do repeated force-length relationships before and after several stretches, which actually reduced the passive force. So we've got, now these are 50 hertz contractions. This is the peak force, not active force. And this is the passive force in 2 different series. Now there's diamonds and there's squares, and there's diamonds and there's squares up here. The peak force didn't change, the passive force did. Why would active force change? There's no explanation for it. So you don't subtract this force from this one to get active force. You'll get the wrong value. And the next graph here shows you what's happening with length, fascicle length, during a contraction. Now, these, I'm not sure, they're probably 50 hertz contractions, but they could be completely fused tetanic contractions. So actually, they're more likely to be that. But the initial length is here, and the force will increase and decrease. The passive force started very high. At a shorter length, the passive force is much less, and the fascicles will shorten as the force increases, and then go back to the original length as the force decreases. And then at a shorter length, the passive force is basically negligible, and the force will increase and decrease during a contraction. So my thought is that the passive force is decreasing during the contraction corresponding to the fascicle length. The fascicle length dictates that passive force. So this is what I think is happening. This is the contraction, so that's the measured force, and it starts with a high passive force. You get oscillations here because it's 50 per second in the rat gastrocnemius muscle. It's an incompletely fused tetanic contraction. The traditional way of calculating active force is to assume that passive force remains constant, and then the active force would be this difference. I'm suggesting that the passive force decreases, and this decrease can be estimated by measuring fascicle length during the contraction and knowing the passive force length, passive force fascicle length relationship. And you can calculate that there's a decrease in the passive force, and now the maximum active force should be calculated as the peak force minus this estimated active force. And we quantified the stiffness of our muscle preparation and had Meredith go back and recalculate all of her active force for the data that she had on fatigue. Remember, she had fascicle length, so, and we knew a fascicle force length, fascicle length passive force relationship for each preparation at each time point. This shows you what the consequence is. So passive force is here, and if you do a contraction at this length, the fascicle will shorten, and now you get a peak force up here. And we're saying don't subtract this, this passive force. You need to follow this down and subtract the passive force down here, because that's the length passive force relationship. And so the open triangles show the active force calculated in the traditional way, and the closed triangles show the active force calculated in what we call the corrected manner. And you can see that it really changes the force-length relationship. These are for 50 hertz contractions, and it makes no difference at short fascicle lengths because there's no passive force. So if it shortens during that contraction, the passive force doesn't change, and your active force is the same, whether you do the traditional or the corrected manner. But at long lengths, it makes a big difference. So when Meredith recalculated her data, this is what she got for the fatigue across lengths. Now this is 50 hertz contractions, and what she saw was that there's nearly a parallel decrease in the active force calculated in this corrected manner. So there is fatigue at even short lengths, whereas it wasn't evident in the traditional way of calculating active force. But if you look carefully at this data, there's still an issue, because this value for the fatigued state is only a few percent less than, and actually this one wasn't significant, so I shouldn't even talk about that. Let's go to this one. This is probably still 80% of that, whereas this is 65% or so of that. So there is greater relative decrease in active force at the short length than at the long length. We thought, okay, we're still getting a length dependence of fatigue, even though we're getting what we think is the correct active force, and there seems to be this parallel shift in active force across at least most of the length range. So what could cause this? Well, for years, I've been working on the theory that fatigue was caused by decreased calcium release. And I had often in the past used dantrolene as a drug to inhibit calcium release and see what it does to the contractile response in muscle. Dantrolene inhibits calcium release from the sarcoplasmic reticulum. So in my mind, it mimics fatigue. And I'd actually published a couple of papers looking at some of the contractile properties of muscle, showing that the effects with dantrolene are very similar to the effects of fatigue. So we did another little study. This one was with Meredith again, but it was also with an undergrad student, Jennifer Campbell. And we basically looked at 50 hertz contractions before and after fatigue, and before and after dantrolene injection, and we tried to get a dantrolene injection that would cause as much decrease in the twitch force at the reference length as the fatigue caused. So we were trying to match the decrease in twitch force. And this basically, it shows that the relative decrease in force is greater at short lengths than at long lengths, and that the effects of dantrolene are very similar to the effects of fatigue. So you don't need a special mechanism to explain the length dependence of fatigue. A decrease in calcium concentration will actually cause a length-dependent effect. And we know that length in a muscle affects calcium sensitivity. And so that could be the factor that actually contributes to this greater fatigue at short lengths than at long lengths. So basically, we looked at active force. It should be calculated using the passive force expected at the length at which peak force was reached. Length dependence of fatigue can be explained by decreased calcium release, and it's valuable to consider evidence that was not planned. And I think in both of these studies, we had to look at the data beyond what we were intending to measure, and there were other clues to what's going on. The slow component of oxygen uptake does not represent an increasing energy cost of exercise, and heavy intensity warm-up decreases the anaerobic contribution in a subsequent bout of exercise. And with that, I'd just like to give my acknowledgments. I've talked predominantly about 3 master's theses, Meredith McNaughton, Jessica O'Connell, and Jamie Weir. And Sports Science Association of Alberta actually funded the work on the slow component of oxygen uptake. And NSERC has funded my research pretty well since I first got here. Thank you.
Brian, questions? Brian?
Brian? I'm wondering if there's any way to measure fascicle length in intact humans when they're exercising to adjust for the change in force.
You can use ultrasound imaging to do that, and Glen Lich work has actually done that for the medial gastrocnemius muscle, and he basically took our method and translated it to the human and said, this is what you have to do. I'm not sure he did as thorough a job at estimating the passive force as Jared has done, and Jared has done the same thing, looking at active force using the correct manner of estimating active force. The problem with passive force is that when you have a human limb in a Cybex, you have to subtract a gravity effect, and sometimes if you get that wrong, it impacts your passive force measurements, which are pretty low. And I think in human muscle, the passive force is pretty small through most of the joint range of motion. So it's probably negligible. And I want to say that what I'm saying here about calculating active force doesn't change much of what we know about skeletal muscle, but it probably does impact a few papers where measurements have been made at a long length where passive force is present or is substantial enough to make a difference. But in human muscle, and most of it is, passive force is pretty low.
Okay. We did the same muscle measurements in a preparation for the series elastic components. See if it's.
I didn't have to, and actually, the first paper that Meredith and I wrote together wasn't her fatigue paper. It was the second study that had the two tests to evaluate how to calculate active force. And we first submitted it. It was sent back with a comment that Jewell and Wilkie did this in 1958. And so we hadn't seen that paper, and we went back and looked at it, and sure enough, they had done something similar, and they showed that when you calculate active force, it's okay to subtract the passive force measured right before the contraction, but they used an isolated muscle with no tendon, and it was a parallel fibered muscle, so basically no series elastic property, and so there's no need for correction. And the other situation where there's no need for correction or no change in fascicle length is what Gordon Huxley and Julian did when they did their classic force length relationship, and that was they used a feedback control system to keep a segment of that muscle at a constant length. And so fascicle length wasn't changing, or at least segment length wasn't changing, and the way they calculated active force in the traditional way would still work.
So in a skin fiber, the same thing doesn't happen?
Sorry?
In a skin fiber preparation, does the same thing not happen?
In a skin fiber preparation, you're dealing with relatively low passive forces. So if you're stretching it out where you're getting substantial passive force, you're probably approaching no overlap of the sarcomeres. I mean, maybe Venus can address that, but would that be reasonable to say passive force is not a huge issue in skin fiber?
In psoas fibers, it starts at about 2.8.
Okay.
So
But
if you stretch, it starts like earlier
Okay.
than beyond the micrometer.
Okay. And actually, so then the issue is your preparation will determine whether or not those sarcomeres are shortening during contraction. And some people attach the ends of fibers in a way that actually adds to the compliance. There might not be tendons there, but the sarcomeres at the end get stretched while the middle ones shorten. But other methods of attachment actually minimize that. So you have to look at your preparation to see whether or not you need to take this into consideration. And I think with your gluing preparation, there's very little shortening. Is that correct?
Should be.
Yeah.
So I'm curious about the traditional method because I'm not familiar with how it's done, but I sort of always assumed that the whole idea is to subtract out the passive force length curve, which has length dependence. So if you activate the muscle and the fascicle length changes, shouldn't you naturally want to subtract the force out at the length at which you measure the force?
Yeah.
Why wouldn't you, or why would you use the previous length instead of the actual length?
Because in 1958, Jewell and Wilkie said it's okay. And nobody stopped to think, but that was in a preparation where the fascicles weren't shortening. They just blindly followed. And it's, mass following, except for 4 papers.
Okay, but I think if you just ask a grad student to do this, and you just explained there's a force length curve, a passive force length curve, and there's an active curve, you said try to account for this, and they didn't know about the traditional method. They would just do it the corrected way, right?
But you need additional information to even think about it that way. You need to know that that fascicle was shortening during the contraction.
But they're measuring that, aren't they? I mean,
Well, not always, no. No, and actually measuring fascicle length in our experiments was relatively
don't
new.
people try to get rid of the series component so that
Yeah, and in our paper where Meredith and I talked about this, we said that most physiologists deal with this by studying muscle with very little tendon in series. And if you look at all of the single fiber work in like Hill and Edmund, they always clamp really close to the muscle fibers so that there's very little tendon. And so they knew about this, but over the years it seems to have been kind of lost and not considered. And like I said, there were 4 papers that we found that actually did subtract the passive force measured at the sarcomere length or fascicle length at which peak force occurred. One of them was Hector Kurz, who was actually here at the University of Calgary, and one of them I think was Bobbert, who was here as a postdoc many years ago, but now in the Netherlands. So strong Calgary connection in terms of understanding muscle.
Yes.
So what do you think about the calcium sensitivity and the traditional way of calculating the active force? So are we underestimating also the calcium sensitivity effect from stretch?
I think so, and in fact, I don't think it's evident, and it's not in any of the graphs that I showed, but when we look at the tetanic 50 hertz and twitch contractions.
What's the question?
Oh, sorry, she's asking whether length-dependent activation is affected by the way I'm calculating force versus the traditional way. Length-dependent activation is an issue where the force-length relationship for maximally activated muscle will give you one dome-shaped curve, and if you measure it with submaximal contraction, that you get another dome-shaped curve, but it shifts so that the peak occurs at a longer length. And so it looks like optimal length shifts as you decrease the intensity of activation. And the classic paper that dealt with this issue was Rack and Westbury back in 1969. And they showed a huge change in what appeared to be optimal length for tetanic versus submaximal stimulation. And they did not calculate their active force, as near as I can tell, in the way that I'm suggesting. They did it in the traditional way, which means they underestimated the active force at long lengths. When I look at submaximal activation versus maximal activation, I still get a difference between a difference in optimal length, but it's very small, not huge like Rack and Westbury see. So I think it does affect the length dependence of activation, or at least our interpretation of it. Okay. I think it's still real. It's just much smaller than we thought.
Does the passive force depend on the speed of the length change, or only on the length?
I assume that it's just the length change, but I guess if you had a really fast length change, there might be some hysteresis in that. Yeah, but it's hard to know because you can't separate it out once you have length change. I guess you could do it passively, but you can only do it stretching, because as soon as you do a fast shortening, passive force would drop very quickly. Yeah, so there is hysteresis in it.
Yes, Frank?
When looking at the slow rise in oxygen uptake, for athletes, would it be beneficial for them to try and improve, like train their ventilation specifically to improve that or reduce that slow rise? Or are athletes doing that at all?
Maybe Guy could answer that. I know lots of people have looked at training the ventilatory muscles, but unless you're a situation where the muscles were impaired in some way, I don't think it makes much difference. Is that?
I think it
It does?
Yeah, it does. I mean, if you talking specifically about the increase of oxygen due to increase of oxygen concentratory cost, I'm not too sure, but in terms of the effects on performance, for sure it works. Especially for exercise like that. Like you're rowing or track cycling typically. And I actually gave a power grade to Jessica a few years ago because she wasn't doing that. I'm not sure if she never told me if she used it, but I think it works.
You're just saying you can pump more, but that doesn't mean the cost is.
But if you train your respiratory muscle, they fatigue less, so they should deteriorate less their efficiency. So in theory, the oxygen cost associated with respiratory work should decrease.
That's only if fatigue causes a decrease in efficiency.
And that's actually that was actually my question. So because I wasn't aware about I was aware of Jessica's results obviously, but not Jamie's results. And so what you're saying is not only with fatigue you don't have a decrease of efficiency, but you have an increase of efficiency.
Well,
and so what would be the reason for that? Is it significant? Do you have a significant reduction of total?
I think it was a significant decrease from the first 3 minutes to the next 2 3-minute segments. I don't think it's related to fatigue. I think there may be something in initiating the activity that makes it a little more challenging or difficult, and that's why the total energy cost was higher. Or we're overestimating the immediate energy system contribution. It's either of those two. To deal with the fatigue, I actually did a project many, many years ago as a graduate student with Bruce Gladden, where we measured oxygen uptake in isolated dog muscle. And we measured oxygen uptake for a series of contractions that were either twitch contractions or double pulse contractions or contractions after fatigue that were either single pulse or double pulse. And we might have even done some dantrolene in there. That was when I first started using dantrolene to mimic fatigue. And the relationship between oxygen uptake and force, now this isn't efficiency, it's a measure of economy of force production, straight line relationship for each animal that was a correlation of 0.99, so huge linear change in oxygen uptake for force, regardless of how we changed the force. So you cause fatigue, you're still on the same line, which basically means the energy cost to maintain force is the same in the fatigue state as in the non-fatigue state.
But here you're saying that it's not constant, it's improving. It's improving.
Well, no, I'm saying that's unrelated to fatigue. When you go from the first 3 minutes to the next 3 minutes, I think there's something about the movement that actually the energy cost is coming down. I don't think it's related to fatigue.
But you started from rest, right? Like,
yeah.
From 0 revolution per minute, so maybe that's a few seconds, is what you're saying?
Yeah.
So why does the ventilatory cost go up? Because you're saying it's not a free.
The ventilatory cost goes up because you're increasing ventilation. So the work of breathing is more just because there's more air going in and out.
My question was, could that change in efficiency in the first 3 minutes be because to initially power that bike up from a rest state to the speed at which they're going to have to exert more force, and then the requirement of more force would use faster twitch muscles, which are less efficient?
It could. I mean, the only way to test that would be to have a bike that's pre-accelerated, so there's no acceleration involved.
Exactly
yeah.
Do you think the method that you're using is sensitive enough to detect that?
No, I don't. And I mean, there's some error in oxygen uptake measurement, but it's not large. The error in the immediate energy system is probably substantial, and the error in the lactate actually. It's interesting. DePrampero is the one who gave us the background on that, where we use an equivalent of 3 milliliters of oxygen per kilogram of body mass for each millimolar increase in lactate. So that's the equivalent to calculate an oxygen equivalent for lactate accumulation. And Bruce Gladden did a study many years ago, and he suggested that number should be 5.4. Nobody has followed his suggestion, and lots of people have followed DePrampero, so we did too. But whether or not that value is correct, we don't know. oddly enough, it doesn't matter in our calculations because it just increases the anaerobic contribution everywhere, and there's still no significant change between the 3 to 6 and 6 to 9 minute values. We actually calculated that.
So you also showed some curves of force length going up and coming down, and I'm just curious what's the explanation for the loop?
That's just hysteresis. So that was fascicle length measurement versus force for 3 contractions at different lengths. Is that the one you're talking about?
Yes. So hysteresis, how? Like, it's friction, it's, fluid, it's, what is it?
It's hard to say. You're basically shortening the muscle, causing that increase. So if we do it, well, let's do this one. So as the muscle shortens, the force will rise, and then as it relaxes, the force goes back down, and the length change isn't as fast as what you would expect. Whoops. The length change just isn't as fast as what you would expect, so, or the force change is faster, depending how you want to look.
Why?
Yeah, I don't know.
The question for Brian?